Justin Miller, Oxford College of Physics here, and we are going to look at some more physics-y stuff. So what we want to discuss and understand at this point is what is known as center of mass, or sometimes interchangeably center of gravity. We're going to stick with center of mass right now, and then we can talk about the difference between the two, that it is possible. All right, so center of mass, what is it? Center of mass is ultimately like an average value of the mass of an object weighted by its mass. So that sounds a little confusing, but ultimately it's a matter of breaking an object into individual mass elements and saying what is the position of the average of all those elements weighted by the mass of the individual elements themselves. So the center of mass is a position, and we can ultimately trace it to a three-dimensional coordinate system in which there is an x position, a y position, and a z position. We'll mostly just stick with x and y, two-dimensionalized things, but really it's just a matter of where are the individual mass elements and what's the average value then. So for a system of discrete masses, we'll just say in 2 dimensions, center of mass is given by xcm. This is going to be the x position of the center of mass, is equal to 1 over m total times the sum from I equals 1 to n of m sub I x sub I. So what do we have here? Well, we've got the individual mass elements and their individual x positions that we're adding them all up. And then we're dividing that by the total mass, and that gives us what the x position of the center of mass is. So position along the x-axis of the systems, I don't want to say object necessarily, but systems and total is the total mass of the system. M sub i's really are individual discrete mass elements at positions x sub I along the x-axis. I shouldn't necessarily say along the x-axis. Yeah, x-axis, maybe not the best thing to put in there, but along the x-axis, that's okay. Positions x sub I. We'll just leave it at that. And then we can also have for y, the position of the center of mass along the y-axis is equal to 1 over the total mass times the sum from I equals 1 to n of m sub I y sub I. So we got the same sort of thing, except we're looking at the individual mass elements and their y positions to figure out what the center of mass position for the y position is. All right, so how does this all play out here, right? Well, if we could look at something sort of more one-dimensional and think about a couple things here. So it's kind of, again, the average value of the position of the masses weighted by the total mass of the system, or weighted by the individual masses. And as it turns out, that as long as we're in a uniform gravitational field, the center of mass and the center of gravity are defined the same way. And it's nice to think about center of gravity because we can think of the center of gravity as the point at which gravity acts on the entire object, an isolated single point. Even though it's distributed across the total object, there is a position on an object that we can balance things out. So I can generally find a balancing point on an object. Let's do something like this and say, right now, it's as if gravity's pulling down on this point right here with the force mg, and I'm pushing up on that point right there with the same amount of force. And thus it's in equilibrium. Well, yeah, truthfully, gravity is acting on this whole thing, pulling it downward, every little mass element, but it's as if, again, that there's one singular point that I can idealize gravity acting on. And that's the center of gravity. So, again, with the gravitational force being uniform for the most part, we can also say that that's the center of mass. And it turns out that things want to rotate about their center of gravity or their center of mass in a uniform field. So it's another way of finding it. I could take this and spin it. Oh. And what does it rotate about? It rotates about its center. Why? Because the center of this object is where the center of mass actually is. Well, what about something like a hammer here? Hammer, where's the center of mass of this? Is it the center? And well, it kind of depends the orientation. I could say that I could balance it like here, and there's an axis that goes through it this way that defines the center of mass. But I also could balance it, well, if it's not here in the center, it's going to be over here. So let me try to get this here. Boom, it's about right there. So what we have is the center of mass along this direction is right around here, right here. Why? Because the top's much more massive than this other side over here. The head of the hammer is much more massive. It's steel, while the rest of it's not steel. Anyways, or at least it's hollow. If I were to spin this, where does it spin relative to? It spins relative to its center of mass here. This is where it wants to spin around. So if I take it, it spins or rotates about this point here. And let me try to be a little careful with this. Well, you can kind of see that, right? It spins about here, right? Well, that kind of goes for everything. So I could start taking something like this and say, well, what happens if I spin this? What do I think the center of mass is about the plane of this object here? You can probably say that's probably at the center, and I spin it. You can probably see his nose kind of stays in the same place because that's right about the geometric center of this. And if I could maybe try to balance this about the center, but that's it. Instead I spin it this way, well, the center of mass cuts through the middle of it. The intersection between those 2 points is where the actual center of mass of this object is. So if we've got something that cuts directly through the middle this way, directly through the middle this way, the true center of mass is where those two axes, if you will, intersect. But it's all about the individual mass elements that comprise this object, which are a bunch of atoms, right? And where they're located relative to one another. And that kind of gives us the center of mass thing here going on. All right. I could also take something like this rod again, as I said, hey, the center of mass is right here. But what happens if I change the mass distribution of this rod? What if I say, I'm going to make this side towards the top much more massive than it is right now? I can take a nice little mass here and fix it onto the top here, the help of a nice little clamp. So where's the center of mass now? Well, it's not in the center anymore. If I try to hold it right here, it just wants to rotate. If I let go of it, because, well, there's going to be a non-zero torque on it. That's what we're getting to. But anyways, the new center of mass is right about there. If I were to throw this up and spin it, it would rotate about this point right here instead of the center as before. Why? Well, if I've added another mass, added another location, and it shifts where the center of mass of the object is. All right, so we can do something kind of simple here, and we'll get to the torque part that's good to be looking at with this. Anyways, if we went ahead and just said, for instance, we've got ourselves, say some M1 is equal to 3 kilograms, and some M2 is equal to 5 kilograms. And this is at the position, we'll just say 0, 0 meters. And this is at the position of, let's say, 3, 0 meters. So these are point masses that are on the x-axis. You can kind of put those and say, oh, we've got one mass right here. There's our M1, and then 2, 3 meters over here. We've got an M2. It's much more massive. If these were not hinged together, but connected together with something that was massless, or I just wanted to say, hey, where's the center of mass of this system? Well, we could go ahead and start applying what we have up here. So if we take this and apply this XCM is equal to 1 over M total, multiplied by the sum from I equals 1 to N of M sub I X sub I, that's going to give us 1 over the total mass, which is M1 plus M2, multiplied by the sum of these indexes here. So we've got, that's going to be multiplied by, well, we start with I equals 1, M1, X1, plus M2, X2. So if we come back up here, this is X1, this is X2. Those are the X positions of those individual masses. So if we go ahead and throw this all in here, we've got ourselves X1 is equal to 0, X2 is equal to 3 meters. So we've got 1 over 3 kilograms plus 5 kilograms multiplied by 3 kilograms times 0 meters plus 5 kilograms times 3 meters. So hopefully we could go ahead and get this going pretty easily here, and we've got ourselves 15 kilogram meters divided by 8 kilograms, which gives us 8 15ths, 7 eighths, 1 7 eighths meter is the position of the center of mass along the x-axis. So if we went ahead and cut this in half, we'd say, well, if this is 3 meters right here, 1.5 meters would be about there. 1 7 eighths, almost 2 meters, so we could kind of say, well, 0.75, 1 half, 2, maybe it's a little bit more over here. XCM. Within feasibility there. But there's the center of mass of this. It's not just in the middle of it, because it depends on the actual masses themselves and their positions. It's pretty simple, pretty straightforward, figuring out the center of mass for a system of point masses, or discrete objects at that. All right. So what we want to be able to do with this is sort of utilize some of the ideas here for when we're talking about torque. Because when we take an object, we can balance it on something like a fulcrum about its center of mass. So this meter stick, pretty nice continuous mass distribution, may not be completely uniform, but it's pretty close. So I'm going to put this little pivot point at the geometric center of this at the 50 centimeter mark. I can put it in here, and if I can get it at its center of mass, it'll stay balanced. Notice it doesn't stay balanced right now, right? It tilts that way. Oh, yep. So that means that this side is a little bit too much, a little bit too heavy, so just slide it over a little bit that way. See if we can get that to balance out. That looks pretty good. Yeah, that looks really good actually. So this point right here, right where I have this little clamp, in a sense, this fulcrum's pushing up right there with the same amount of force that gravity's pulling this entire thing downward. This is why it's an important aspect, center of mass, center of gravity, because we can think of it as the one single point that gravity is acting on the entire object. I push up on it at that point with the same amount of gravitational force, we got balance, balance. But what happens if we don't have this wedge, this fulcrum at the center of mass of the object? Well, it changes things, The center of mass stays right here with respect to the object. If I go ahead and push this over here, the center of mass doesn't change regarding this object right here. The center of mass is still at the 50 centimeter mark. What happens if I let go of it? Well, we could think of gravity acting on this the entire mass of this meter stick at this point right here. We got an axis of rotation, and we've got a point of application of a force. That point of application is right here at the center of mass, and the force is the gravitational force. What does that constitute? Well, it constitutes a torque. So if I let go of this, what's going to happen? Yeah, it accelerates downward because there's a net torque on it. So that's something that's important to be able to consider, in that we can have an object that exerts a torque on itself due to its location of its center of mass. Now I could start balancing things out, move it further away, that's fine, but I could start taking some little hook things and some more mass over on this side and find a point that I can get this to balance out. So the force of gravity acting on this hook with the mass pointed down on this side is balancing out the torque that's due to the force of gravity acting on the center of the mass of the object pointed down this way. This one's producing one torque, this one's producing another torque. Now, they're different radial distances away and they're different masses, but that's how torque works out, right? It's not just the mass, it's not just the force, it's where the force is being applied. The radial distance away from the axis of rotation. So, again, this is why it's important to be able to think about the center of mass of an object and be able to know what it is, especially when we're talking about systems in balance, where we've got equilibrium, but we've also got the center of mass of the object may be exerting a torque on the object itself. And you've got to take it into account. That's it. So, pretty cool little system here. In this orientation, some things to point out: the force due to gravity is completely tangential here. We got the radial vector pointing this way. We've got the force due to gravity that way, which is just the mass of the meter stick times g. And then the cross product between those two just gives us mgr. And there's the torque that it produces. And your reference frame, you could say, hey, that would tend to produce a clockwise rotation. So we could call this one a clockwise torque. This one, we've got this total mass here, which is about 150 grams, located at some distance away from the axis of rotation. So we'd have another mg times a different r, and that's producing a counterclockwise torque. And if we went ahead and did some computations here, we better find that the torque on this side is equal to the torque on this side. They're producing opposite directions, or they have oppositely directed torques. Net torque is equal to 0. Whoosh. Equilibrium. Equilibrium. All right, so that's kind of the idea with this. Not too bad. And we'll just kind of leave it at that for now. All right. Until next, take care and be careful spinning hammers around.